Okay, so our last talk for today is going to be Hunter Mills and Justin from UCSF.
Hi, I'm Hunter. I work at the Bakar Institute at UCSF, and I'll be talking to you about a recent project we've been working on to use machine learning on UMLS terminology to classify hip fractures from clinical notes, and this was done using the Information Commons platform at UCSF, and I'll be co-presenting with Justin. So, yeah, good. So as an intro, the Bakar Institute we focus on computational health science at UCSF and work in aiding other researchers, perform data analysis and help with solutions. And one of the major projects we're working on is something called Information Commons, where we're creating a large de-identified multi-factor data store that also has some big data and ML tools. And that helps a lot of the complications with IRBs and just the rigmarole that you have to do when working with patient data. And Justin will talk a little bit more about that in a little bit. And right now, Information Commons is in beta, where we have some structured data, and we're working to get notes up and running and get notes in the future, we have structured data currently. We're working on getting notes up and running, de-identified notes, as well as de-identified images, as well as providing extractions for notes. And I guess I don't really need to go over information extractions. I think we've all heard more or less the overview of what that is, so I can pretty safely, I think, skip this slide. And I guess we'll hand over to Justin real quick.
Thank you. See how that works. So again, I'm Justin Krogue. I'm one of the orthopedic surgery residents at UCSF. And so we've been working on a study looking at fracture identification. This actually ties in very nicely with Dr. Sohn's talk. Using computer vision. So kind of the motivation for the project, our fractures are very common. Specifically hip fractures, there's 250,000 a year just in the US. While they're also very common, they're also some things we think, common things aren't a big deal, but in the case of hip fracture, that's not true. There's actually 30% one-year mortality. So a couple interesting stats. Your mortality after, one-year mortality after hip fracture is actually similar to high-stage cancer in a lot of cases. And actually a woman, I think in her 50s, is as likely to die from a hip fracture as she is from breast cancer. So it's a very common problem. And one interesting thing about hip fracture is that the timely diagnosis is actually very important. So we don't often think of fractures as being a critical finding that maybe would be called by the radiologist about as an urgent finding. But in the case of hip fracture, there's actually a recent paper that came out that showed that even a 10-hour delay in getting from their fracture event itself to the operating room leads to a 5% higher mortality rate. And that's a well-controlled study, again, controlling for factors that may lead somebody who's maybe more medically comorbid to take longer to the OR. So we know that fractures are important. We know they're common. We know in the case of hip fractures, actually diagnosis time affects outcomes. We also know, last point there, that missed fractures are actually the most common reason for ER litigation. So even if you don't affect outcomes, at the very least there's financial motivation to get fractures right and do it quickly. Interestingly, for hip fractures as well, their subclassification dictates entirely their operation. So another step in hip fractures, you can actually not only potentially shortcut the time it takes for diagnosis, but you can actually even immediately notify the orthopedic surgeon and the operating room staff if you know what kind of hip fracture this is. So I can show the next slide what that is like. So on the left-hand slide, you can see 3 fractures. The top is a femoral neck fracture. The middle one is that same fracture but displaced. And the bottom fracture is what we call an intertrochanteric fracture. And on the right side of that 6-pane image, you can see the 3 different surgery types these patients would get. And those essentially entirely come from what pattern of fracture that they have. So you can see our process for labeling images here on the right. We just use kind of a browser-based lightweight annotation software that we've modified for ourselves, but to draw a bounding box and then give individual labels. We have been doing this for a little while now. We have labeled about 3,000 hips, and our model is achieving about 92% accuracy, which in our studies comparing to humans seems to be about expert level. But what's interesting and what motivates our collaboration with InfoCommons team is that this is again off 3,000 hips from about 2,000 studies. There are actually 22,000 x-rays obtained in the emergency room, so ones that would be relevant for our study at UCSF. And obviously, that's 10 times potentially the hips that we have. It could potentially take us maybe even greater than expert level accuracy. Even more interesting is that there are actually 3 million distinct studies of X-rays at UCSF. Again, those studies would contain about 6,000 images. Each image may contain 2 hips, right? So not hips in this case generally, but these are all over the body studies. So you can imagine here we're talking about on the order of, at least in the single millions, maybe tens of millions of discrete X-rays taken at UCSF, all of which have been annotated with a professional label already by our radiology colleagues. So as we're thinking about this and thinking about generalizing our results from hip fractures to all fractures, clearly the thought came up and the impression came up, as Dr. Stone touched on, that if we could use natural language processing to automatically classify these reports by fracture and fracture type, then we could short circuit this process and instead of training on 3,000 X-rays, be training on potentially millions of X-rays, and maybe even create a data set similar to an ImageNet data set. We did a first pass ourselves using just the radiology reports, and we obtained good performance on our data set that we were testing on, but when we attempted to generalize to a new data set, did not achieve good success. And that kind of takes us to Hunter's group, what they've been doing with information commons.
Thank you. Yeah, so we came up with a little hip classification pipeline where we ended up taking in a labeled set that we got from Justin and Valentina's group, and ended up, instead of just grabbing one note from medical database, we grabbed all the notes in a time frame. In this case was 8 days, and then ran each one of those notes through CTakes, which is a clinical term extraction tool, which I'll go into in a little bit, and then take the output of that and running it through an ML pipeline to predict a label. As a little bit of a background, UMLS, which I think I've heard people say that a little bit on and off today, it's the Unified Medical Language System. It's a compendium of medical terminology, so your ICD codes, your SNOMED, RADLEX is another one. And this links all the vocabularies together via something they call a concept unique identifier, and this can include one-to-one relationships, one-to-many or many-to-many, is maintained by the National Laboratory of Medicine. And then CTakes is short for Clinical Text Analysis Knowledge Extraction System. It's an NLP pipeline to extract CUIs and to detect negation as well as many other things, and is managed by Apache and initially came out of the Mayo Clinic. And as a quick aside, we'll go into the info common structure a little bit again, where it's a de-identified data store that includes clinical data, medical images, structured data, and with the clinical notes and all this, you can start to kind of build a, kind of a story where how a patient's bouncing around, where they can start in the emergency room, go to radiology, and go to surgery. And then we can extract all the notes from all those encounters, not just one encounter. And so the CTakes pipeline, we ended up taking all the notes for a given patient, running them through CTakes, and then creating a bag of words. So just extracted all the CUIs and prepended them with a true or false label, whether they were negated or not. And then ran that through an ML pipeline, where we looked at we created a term frequency vector and looked at the 250 most common CUIs in the data set, and then performed ML on that and got fairly good results. So using a multi-layer perceptron, which just could have been any of them, this is the one that just happened to perform well. When the data set was balanced, we had really high accuracy of 98% and high recall and F1 score. When it was imbalanced to something more like when people have fractures that would actually come into the clinic, so it would be more like a 10-to-1 ratio. Still had good accuracy, but definitely things dropped a little bit. And with just simply oversampling the fracture cases to even it out, we got a good amount of the precision and recall back. And so this leads then to what could be next for this project. So it could be things of making this model better, which could involve feature engineering or leveraging the actual ontological relationships in the CUIs, so we could back off from the specialized fractures and actually move up from like the internal rotated type things to just hip fracture. Or we could extend the scope where we're now including not just NLP, but include X-rays in the classification and the structured data. Or we could look to generalize the classifier to include not just hip fractures, but a general fracture classifier, as well as different different applications with different groups, such as cancer immunology, pulmonary diseases, or prostate cancer. All right, thanks. Any questions? Yep.
Is this similar at all to what Cure.ai is doing, or have you guys heard of them?
I'm not entirely aware of Cure.ai.
Okay, it's spelled with a Q, and it's
Okay.
in India, and they've had some traction on NLP plus images for NLP.
Any other question? Okay, great. Thank you very much, guys.